A flip-flop circuit is a fundamental model of a memory device. But there are some concerning issues as well regarding these conventional models. Firstly, volatile memory. It means that a circuit must always be turned on to store its data. As soon as the circuit is part off, the data are erased. Secondly, power consumption. To implement the logic gates involved, several transistors need to be implemented that require considerable amount of power supply. Thirdly, scaling limitations. This whole setup is designed just to store one bit of data. That is another matter of concern. All of these issues can be resolved if we use a memristor. A memristor consists of three thin films compacted like a sandwich. The middle layer is called switching layer. The top and bottom layers are called top and bottom electrodes respectively. The heart of the memristor lies in the switching layer, typically composed of a metal oxide like titanium dioxide. The top and bottom electrodes are usually made from inert or reactive metals like platinum and titanium. The layer thicknesses are at nanometer scale, that is why they are called thin films. The memory writing operation of a memristor can be classified into two categories, namely set and reset processes. Let's talk about the set process first. Here the atomic arrangement of a memristor is schematically illustrated, where the blue atoms are titanium, orange atoms are oxygen, and green atoms are platinum. A power supply is introduced where a positive voltage is applied to the top electrode and a negative voltage to the bottom electrode. The applied voltage is around 2 volt. In spite of such a low voltage, because of the nanometer scale thickness of the film layers, the working electric field is very high. Due to the very high electric field, the oxides of the switching layer migrate to the top electrode and accumulate at the interstitial sites near the interface. As soon as the oxides leave, vacancies form at their preceding sites. The oxide releases its electrons after reaching the top electrode, and the electrons go to the positive terminal of the power source. Electrons released from the negative terminal goes to the bottom electrode. Because of the oxide vacancies at the switching layer, a net positive charge is created. And to balance this net positive charge, the incoming electrons from the bottom electrode accumulate at the switching layer and moves through the titanium cations, leading the switching layer to N-type semiconductor behavior. Due to the applied electric field, the available electrons give rise to the electrical conductivity of the switching layer. These phenomena ultimately end up forming a conductive filament across the switching layer. The current state of the device is called the low resistance state, which can be considered as binary 1, or we can say the device is on. Even if the power supply is withdrawn, the state of the device persists. That means this device memory is non-volatile. During this on state, the structure of the switching layer stays non-stoichiometric. Reverting to the previous state is called the reset mode. In this mode, negative voltage is applied to the top electrode and positive to the bottom electrode. The conductive filament breaks down and every other phenomenon is reversed. The current state of the device is called the high resistance state, which can be considered as binary 0, or we can say the device is off. Now let's explain the entire phenomena graphically. Initially, the device was off and no significant current flow can be observed with increasing voltage. After reaching a critical voltage, the device gets on, that is equivalent to writing 1. Now noticeable amount of current flows across the device for the applied voltage. To reset the device to off mode, a critically negative voltage needs to be applied to revert the entire device's state, that is equivalent to writing 0. Lastly, if we have to read the stored data anytime, a small amount of voltage is applied and the existing device memory can be used.